This conference will now be recorded.
Okay, so good afternoon, everyone, and welcome back to a fresh new session of market risk modeling. Uh, as discussed in the last session, we will be talking about the basics of. So we'll start off with an introduction to the toolkits, right, for market risk modeling. So before we go on, right, so just let me go a little back in the last discussion in the last session. So one of the things that we had identified, or one of the things we had discussed in the last session, was, the importance of this. So one of the things that we had talked about was the difference that market risk analysis or market risk modeling and validation will have from that of the credit risk model development and validation. So how different is this? How different is this framework or this the modeling methods under market risk compared to what we had seen in credit risk? So one of the things that we see is that in market risk there are two to three important sources. Now, one of the important source which we generally see is obviously the assets. So, like in credit risk, the risk arises from the stochasticity of the cash flows as a part of lending. In market risk, the story is very different. So in market risk, very simply explained, the risk arises from the fluctuations in the movement of the different asset classes, right? So there are different kinds of markets into which different kind of sources of risk uh, or different kind of fluctuations in the market to which a bank often gets exposed to, right? So obviously, so there are different factors, like there are interest rate movements. Then there are so one of the sources of this risk is this risk emanates from your this thing from your movement in the interest rate. Then another set of risk arises from the movement in the foreign exchange rate. So move from different spillover impacts and so on. Now spillover impacts and all these factors are prevalent for credit risk, but the shocks are very specific to a given set of portfolios. For market risk, these channels are very drastic. Like, so the channels through which risk emanates in the market, in the markets is very. I mean, the channels are too many, and and the impacts often tend to magnify. So therefore, from the sources of risk, so if I look into the different kind of the resources, market risk has a greater variation, or they have a greater variety in that in terms of the risk. So over here, what we will try to do is we need to understand the different sources from which where risk arises, and the next thing that we need to understand is how to manage the risk, right? So before we try to manage any risk, so we need to identify how is it that the risk is quantified. Now, if I have to quantify a risk, right, risk, then the first thing that I need to do is I need to quantify the so I need to quantify the price of the asset, because the risk will arise nothing from the fluctuations in the price of the asset. So any asset which is whose price is determined by the demand and supply in the market will fall under market risk, right? So will be a component of the market risk. So over here, one of the important questions which remain is obviously on pricing the assets. And when I talk about the market assets, right? So there are a few important assets which really come to our mind, and one of the most leading assets, or one of the most prominent assets comes to our mind, are derivatives. And it is very important to understand how exactly is it that a derivative is often priced. Now, assuming that you price a derivative, we need to assess the different sources from where the risk arises. Now, the question that comes out over here is that what is the risk in terms of, right? So basically, let's say our price of a derivative today is 100 rupees, and tomorrow it turns out to be 80 rupees. So what is the problem. So what is it? The challenge that comes over here is that because I had actually bought that asset with 100 at a price of 100, and the price has gone down to 80. The price has fluctuated down and it has gone down to 80. Now I cannot sell the asset, because if I'm selling the asset, I'll be earning a huge loss. So the risk arises over here from the recovery, and the biggest challenge over here is that in this case it is very difficult to recover those asset prices as well, because the prices are being determined by the market. It is not only your own only one individual's buying or selling which impacts, or rather, let me put it this way: it is not the fair selling and buying of one individual which affects the market prices. So it will be affected by what the majority of the, or what the agree, or would be the aggregate decision of the aggregate base of investors who are investing in there. So the risk in the asset prices arises from the volatility, right? And the volatility of what? The volatility of returns. So to see how the returns have been fluctuating over the past, and that volatility itself, right, is a core component, or that's what the risk is. And to hedge that risk, we have different hedging instruments, right? So obviously there are three broad questions that we need to address. The first question that we need to address is how to price an asset. So that's a fundamental question. The second question is that how do we quantify the risk in the asset? The third is how do I manage that risk, right? And as a part of the risk, finally, how much of a capital should I set aside? And while the assets are being traded, what are the fair trading practices? How should a fair trade happen? How should, or when does an arbitrage happen? What is the risk-free rate? How does the risk-free rate operate? Why do we need a risk-free rate? And how do the risks, so when and how do the risks emanate from the different assets? So these are some of the questions that we are trying to address as a part of the market risk discussion sessions. So now the first thing that comes over here that we need to understand, that we talk about over here, is that if I have a asset, right? So if I have an asset with me and that asset has a price, so and there's a risk associated with it, and that asset is being traded publicly in the market in one of the indices, then the question that comes out over here is that how do I assess the riskiness which arises from the asset? How do I track the volatility? How do I predict the riskiness? So that is, so one is how do I characterize the riskiness? The second question is how do I predict that riskiness? And third is how do I manage the riskiness? So in order to do all these things, the first and at the heart of it, what we need to describe is, or what we need to quantify is, what exactly is this stochasticity, right? So in order to characterize the risk, the fuzziness in the asset prices, what we need to ideally talk about are the quantitative concepts. So over here, there are two things which we need to talk about. The first set of things to characterize the risk. So how do I characterize the risk of an asset? How do I characterize that stochasticity? So for that, there is a, so basically we would be adhering to a set of basic concepts, to some basic concept from a stream of finance, which of quantitative finance, which we call the stochastic calculus, right? So we'll talk about the Wiener process, we'll talk about martingales, and there are a lot of different factors around that, right? The second question that comes out from there is that how do I predict the riskiness? And that's where all my predictive methodologies, like all my regression frameworks, my time series regression, my linear regression, non-linear regression, and all other class of linear models, or all other class of regression models will be coming into play. And that's where we need to understand how this arises. Now if I were to use these methods, and in fact, one of the final objectives of building this mathematical framework and building this econometric framework is to finally understand how to develop a VAR model, right? How do I develop a econometric VAR model? So generally what we do is we generally calculate the VAR, right? Using a percentile approach. But the question that comes out over here is that if I were to build a VAR model, which would help me predict the VARs over a period of time, then how do I go about building that econometric VAR model from scratch? That is one of the important things, that is one of the important ideas that we will have, or that will be one of the key objectives of this particular module. How do I go about creating that, developing the VAR model? Right. So that's where a part of statistics, a part of mathematics, and above all, a very important role of probability theory will come in. So therefore, we will have three broad groups in which we will be dividing these discussions. So one of the groups will be to talk about calculus, the mathematical basics of calculus and optimization. We will not be going very deep into them. We will just be talking about some basic functions, like we'll be talking about an exponential function. We will kind of talk about a logarithmic function. We'll talk about a sine function, cos function, things like that. So basically, what we want to do is, and we'll see how exactly is it that these get that we can simulate them, right? So how is it that these distributions can be simulated? How do they look like? What is the function? What are the key concepts related to a function? Then we move on to talk about limits, continuity, differentiability, and from there, what we talk about is that how the so what we talk about is that how is it that optimization happens, because every time you are trying to price an asset. So let's say I'm trying to do an option pricing. I'm talking about the Black-Scholes-Martin model as well. So that's a very critical model in this financial domain. So in the domain of market, we'll talk about the Black-Scholes-Martin model. So the question that comes around there is that how do I optimize the Black-Scholes-Martin model? How do I optimize how do I price that asset? How do I find out that trajectory of the asset classes? And so basically that's a differential equation that we have with the Black-Scholes-Martin model, and we need to solve for that. So every time there's always a stepwise solution that we look into. So the question that comes out there is that how do we do that, right? And at each stage, what are we trying to achieve through that? So those are the questions that we try to answer. So let's say if I have to price an asset at, let's say I want to price an asset at a fundamental price. How do I calculate the fundamental value of the asset? Right? I have to price an option. How do I price that? So for all these things, one basic set of knowledge, understanding that we need to have is that of basic calculus. So we start with functions, we move on to limits, continuity, differentiability, maxima, minima, and to differential equations. So this is something that we will be developing, and at each stage. So now the question is that if I am to just start off with this mathematical framework, how do I get an idea of what is happening into market risk? So at each time we will be connecting back the concepts of market of asset to that concept of the market risk, and we'll try to assess that how exactly is it that this thing is going on, right? So then so basically once we have that, and once we have started characterizing the asset, the asset trajectories, the return trajectories, and so on. So once we have started doing that, from there we move to talk about volatility. We bring in the concept of stochastic calculus. So what makes calculus a stochastic calculus? It is the presence of the Wiener process, the Wiener variable. So we talk about what the Wiener variable is. How does this Wiener variable play a role in market risk? And how is it that these things go on? So that's the second part. That's the next part of that's the next extension. Now with the Wiener process, now once we have done the basics of this calculus, and once we have done a bit of this once we talked about this process, now we stand in a part where we can model the volatility. Now, once we talk about volatility, volatility is the key risk of or risk arising from the assets. So that's where we now start looking to, we will try understanding how volatility works, right? And how is it that it can be estimated? How now one of the interesting components that I'll talk about over here is, and I know it's not much talked about, right? So that's decomposition of volatility. Now, volatility can be decomposed in terms of its amplitude, in terms of its existence, in terms of its longevity, and then there are different ways to decompose that volatility. Now, the decomposition of that volatility will actually help you assess that how better can you hedge them. Now, the moment you try hedging those assets, that is where so that's where your hedging instruments like swaps, options, and they start coming in, like your futures and all these things start coming in. The next question that comes over here is that if I have this volatility and there is this volatility, how do I predict that volatility? That is where time series models come into play, right? So that's the way I will try that. That's the way we'll try to build up the entire model, right? So it's going to be quite a quantitative part. It will be quite a quantitative exercise. Now, along with this, there will be a part where it will keep on intertwining with something, because at the foundation, right, there are different components, like there's a delta, there is vega, there are the Greeks related to market risk. And as you start exploring each of these mathematical concepts, you start keep on hitting on one of these Greeks, and that's where we'll talk about that. So the first objective, right? So like when we started off with SAS, we had first done data extraction, then we did data transformation, then we did data like report generation and all, and then we moved on to from there we kind of bifurcated the journey, right? So similarly, market risk as well, we'll start off with these mathematical methods. We'll see their simulations and how to generate them in Excel, right? We'll talk about some financial functions as well, and from there we'll start our part of model development, right? Because there are some questions, some areas, like so one key model that we need to understand we need to talk about, that we need to understand how exactly is it being developed. So one such model is the VAR model. We need to talk about the value at risk model. We need to understand how it is developed from scratch, how is it back tested, how is it stress tested. So that entire part of VAR will be playing a part, right? Now the question, so first it's a set of methodologies, then from there we move on to talk about the different key sources from where the risk arises. So one of the key source of risk that we'll talk about is the interest rate risk, right? So the interest rate risk is one such part where we'll talk about multiple interest rate models and so on, and we'll see how it works. And then the next part that we'll talk about over there is so another key source of risk we'll talk about is the foreign exchange rate risk, and the third set of risk that we'll focus on is the equity price risk or the asset price risk. So these are the three broad risks that we will be talking about in details, right? So out of this one, and also obviously, yes, so if I have to talk about market risk, I have to talk about the counterparty credit risk as well, and the guidelines that determine the development of the counterparty credit risk models. So so that's the way we will kind of proceed, right? So first, what we need to do is we'll start off with the basics from the scratch, and we'll start off with building out the basic tool set, the toolkit, and by simulating each of these basic functions in one form or the other, and we'll see how to do them in Excel as well, right? So mostly in the next set of the discussions, we'll talk about, we will kind of So we will kind of use the word doc for the theoretical documentation part, and for the simulation portion, we'll try to understand how that function operates and all. So we will talk about so we use Excel for doing those simulations and using those results. Right. So at the end of the story, so at the end of this, you would be having a proper document which you can refer to. So as a part of this entire module, we'll try to build up those documents, right? So that is what our objective is. Right. Okay. So let us. So this is where we'll start off, right? And the first and the most basic question that I'll start off with is the definition of a function, or let's put it like this: basics of real valued real variable calculus. We'll talk about both univariate calculus and the multivariate calculus. So even though I'm talking about calculus, and yes, there will be there will be mathematical uh, discussions which will go on, but what I'll try to do as a part of this exercise is I will try to have, or like, so what I'll try to do is I'll try to you know so what I'll try to do is I'll try to make it as intuitive as possible. Okay, so this is the basics of real variable calculus, where we'll talk about univariate and multivariate calculus. Now the basic concept. Now in market risk, one of the one of the most one of the basic exercises is that, so in market risk, one of, so or in, for that matter, for any kind of risk modeling framework, a very important part is the identification of causality. Right, we need to model causality, causal relationships between x and y, between two variables. Let's say the the interest rate and the asset price. We need to model each of the relationships, right? So the question that comes out over here is that what forms the basic basis of this causality. So the basis of causality is defined by the concept of a real value function, right? So over here, the concept that we start off is the concept of a function, or a real valued function. A real valued. So this is where we'll start off our discussion. So in order to define a real valued function, so the first thing is I say that let x and y be two real valued variables, or be two real variables. Now the first question is that what do I mean by a real variable? So a real variable is a variable which has a defined root. So no matter what, so which has a defined, well-defined nth root, uh, nth root, of the number, right? So basically, let's say I'm talking about, or basically, let's say that if I do a square root of that number should give me back a well-defined value. It should not be an imaginary number. So basically, root minus 1 is called an imaginary number. So that kind of a number is always an imaginary number. So such numbers are not considered. So over here, we are considering all numbers from minus infinity to plus infinity, right? We do real variables. So, so symbolically, so mathematically, they can be represented as mathematically. Mathematically, they can be represented as okay. So x belongs to x belongs to R. R stands for real numbers. Now, when I say x belongs to R, this R is a one-dimensional real number. Or let me put it like this, x, y belongs to R. So they are all real numbers, right? So basically what I'm trying to do is I'm trying to take up two, so I have two variables, x and y, where I say that x, y both belongs to real number. Now I am trying to define, what I'm trying to do next is I'm trying to define an element of causality between x and y. That is something that we always do. Let's say I'm talking about, so I'm trying to say that, okay, the price of a commodity today will impact the, or will help us in predicting the price, or will help us predicting the price of a commodity tomorrow. So I will have today and tomorrow as a, so the price tomorrow and price today have a causal relationship between each other, right? So if the asset price today impacts the price tomorrow impacts the day after tomorrow. So then there is a causal relationship between the price with the price in the next period. So that is what is the element of causality. So for example, if say let's say I'm trying to model whether I'm trying to model whether to what should be the predicted limit of the borrow of a borrower on a credit card should be. So in that case, is the delinquency pattern which is acting as a variable. So the delinquency pattern and the credit limit will have a causal relationship. So that determines, or that depends, or that's, so that is what a causality is, right? And functions help us explain such causal relationship between x and y, between two variables, two real variables, x and y, right? So a function, so how do I define the function, right? Let's say the function x, y So it says that the function x to y is a rule such that for each such that for each such that for each xi for each xi which belongs to x, the rule must plot the rule must plot a unique yi there exists a unique yi belongs to y. There is a unique yi which belongs to y. So basically, what this particular function tells me, or what this particular thing tells me, is that that you have two functions. You have x and y, where x and y are two real variables, right? Now, mathematically, they can be represented as xy belongs to R. So the function is a rule such that for each xi there exists a unique yi in the set Y. So basically, what it simply means is that corresponding to one x, the rule must not map two different values of y. So for a given x, you will get a unique value of y, right? So every time you are putting in x, that rule must unambiguously plot a unique y corresponding to a unique x. So basically, what does this mean? So what does this mean? So this implies that the rule must unambiguously map a unique value of y, a unique value of y corresponding a unique value of yi corresponding to a given value of xi. In other words, it means that the rule must be unambiguous. So in other words, every time a given xi is entered in the function, in the rule, the rule must if rule must at every iteration map it to the same wire. Must map it to the same wire, right? So whenever you enter that value, whenever you are entering xi, it will always map it back to the same yl. So for example, let's say I have some rule, right? Let's say I have a rule over here that so such that whenever I enter this enter xi, so for xi it will, or let's say the rule is twice of. Basically, the rule is y is twice of x. So if I put 1, y will take 2. I put 2, y will take 4. Then again I put 1, it will again take 1. It should not take any other value apart from 1. I mean, it should take 2. So it cannot be that first I enter 1, it takes 2. I enter 2, it takes 4. Then again I enter 1, it stays on 4. So for 1, every time 1 is entered, y should have the same value. So this means that, so this is what causality is. So given a rule, x and y will have a certain relationship, right? So this is described as, so how do you describe this particular function, you or this thing? It clearly says yi is equal to f of xi. Every time I write this, this is yi is a function of x. So what it means is, for every time xi is entered, a particular value of xi is entered, yi will all, I mean, corresponding to that, every time the same value of yi will be mapped, right? So this is how a function will look like. This is how a typical function looks like. Right. So just let me, one thing what we'll do is we'll just bold in this thing. So this yi is a function of xi. So over here, yi is the dependent variable and xi is the independent variable. So as, so and the function is the rule. So whenever I enter xi, given that xi is the rule, so this what happens is, given xi, the given the rule, value of y is always computed. So y, the value of yi is always determined by the values of xi. Right? Up to this point, is it clear? Then we'll go on to the examples. Perfect. Okay. So let us try to define this, where where xi is equal to the independent variable and yi is equal to the yi is equal to the dependent variable. Independent variable. So yi is the dependent variable. Dependent variable. So I have the xi is the independent variable and yi is the dependent variable. Right. So now the next question is that how do I or what examples do I have of functions? So any equation that you write, any equation. So we have always written linear equations. We have always written quadratic equations. So those are examples of functions, right? So functions are something where you are trying to explain a relationship between an independent and a dependent variable. So now let's try to assess some important functions. So over here, let me just copy this part. So this is some examples of some illustrations of real value function. Now the next question that comes over here is like, what are the type of functions and why are we even talking about functions, right? So that's the question that we need to answer over here. So the first and the most, one of the most basic functions that we generally talk about is the modulus function or the absolute value function. So that's the first one. The first example that we have over here is the absolute value function. The absolute value function, or as we call it, the modulus function. The modulus function. So this is one of the basic functions that we are talking about. So example one, so first example is the absolute value function. So let's try to see how much is the, so, or let's try to see how this thing works. So over here it is, so absolute value function. So over here, when I talk about the absolute value function, so how does the function appear, or how does it look like? So basically we say that let x, y be two variables, be two real variables. So we say x, y such that, so x, y belongs to R. So such that, so function f of x to y is a rule such that but each xi belongs to x. So yi, the yi belongs to y is presented using the following rule. Y is equal to, I'll write it like this. So yi is equal to the mod of xi. Okay. So this is yi is equal to mod of xi. So where your xi is the independent variable and yi is the dependent variable. Now the question is that what is this function? So this is an absolute value function or the modulus function. Now this is widely used in any modeling methods at times. And when is it used? So for example, I'm trying to calculate the error of my model. I'll use this. I want to find out just the rate of change. I'm not interested about the directionality of the change. I'll be using a mod function. Let's say I want to find out the price of an asset, right? So I'm trying to assess the price of an asset. So that's where I'm looking into this, right? So I look into this particular value and this in this particular case and so on. So whenever I am trying to find out any absolute figures or absolute value, that is where I am always trying to use this function. So this function will always, this function is extensively used, especially for cases when you are trying to capture the proportional changes or you are trying to capture the rate of change, right? All you want to understand is the rate at which your variables are changing, but you are not interested to know the directionality of the change. So that way, this measure or this, you know, kind of, so this function becomes a very useful function, right? Now the question now what is more interesting to look into this function is that this function, no matter what values you enter, it will give a positive value. So the question that comes out is that how is it that this particular function would actually work? How is it that this function can be deployed? Right, so you always have a positive set of value, you always have a negative set of value. So, and whatever values you enter, right, it will always capture that particular value. So it will capture the, or it will always give you the positive of that value. So negative changes, positive changes, it will give you the positive, always give you that change. So you want to find out how much, by what percentage has the price has changed from yesterday to today, it will give you that. So whenever you want to find out any, so when you're not interested in the directionality of the movement, so then this function becomes extremely useful. So the next thing that we'll talk about over here is that how does this function, or how can we crack this function or decompose, like how can we break this function and see how the output of this function is? How does that work? So the absolute value function, the absolute value function works in the following function, in the following fashion. So over here, let's yi is equal to xi if xi is greater than equal to 0. yi equal to minus xi if xi is less than 0. Okay. So over here, what I can see is that this is equal to x minus xi if xi is negative, right? So given that xi remains positive or like non-negative, then yi is equal to xi. On the other hand, if xi becomes minus I, then xi goes less than 0. So this is the next part that we're going to study. So we are going to kind of assess or simulate this function in Excel. Graphs and diagrams. Okay. So what is the basic part that we are talking about over here is basics of real calculus and multivariate. Okay. So over here, this is topic 01. So topic 01 is real valued function. So over here it is the real valued function. So now let us start off with the first function, which is the modulus function, or the absolute value. So let's say this is example 0. Okay. So now over here, uh, let us create a table. So let's say I have this variable x over here. So let's say I have my this condition is -10, right? And I say this is the next step onwards, it's -1. So what I have done is I have generated a series from -10 to +10, right? So over here, I will create the y. Now what does the y do? The y does, if it is a negative value, it returns the minus of minus of that value, else it returns the plus of that value, right? So basically what I'll do is I'll say if then else, if this is less than 0, then the output is minus this, else output is plus this. So now the moment I do this, now what I'll do is I'll use the absolute function in Excel. Right. So one thing you can see that this values, this series and the series that I have created over here have the same value. Right. So basically what I've done over here is I have simulated this series over here. So this is how the series now looks like. Now there is another part to this. So now let us plot this graph and let's see how it works. So I will y-axis plot. So this is the plot of the modulus function. Now, if I do this plot of the modulus function, so this is your x-axis. X-axis, and this is your y-axis. Right. So, and over here, what I have is, so let me just, right. So I'll take this function. So over here, what I'll do is I'll say figure 01, plot of the modulus function. Right. So this is how a modulus function looks like. So what do you think is one of the biggest, so one of the most important characteristics of this function, or what do you think is or should be one of the most important, like what should be one of the most important observations that you can have from this function? Real value function. Yes. So what is one of the most striking characteristics of this function? Okay, guys, before we move on, I'll just take a couple of minutes time. I'll just get myself a cup of coffee and I'll be back. Okay, just give me a couple of minutes time.
This conference will now be recorded.
Yes. So what do you think is the most striking feature of this function? Swastik, Shubham, anyone? Yeah, so you can put your answers in the chat box as well. So that's fine.
Increase or let's say the slope is changing in the same in both the positive and negative direction.
No, it's not about that whether the slope is changing at a positive or at a negative rate. So that's not important over here because it's a linear. The way we have defined this mod function is that it's more or less a linear, like is at a linear state. But the biggest, the most striking observation of this point is not the amount by which it is changing, but the very fact that it is flipping the behavior at this point. So as you go on to zero, so at zero the behavior flips, right? And that creates a kink in the behavior. So this graph, so this function is not a very smooth function. So the so basically, if you are trying to create functions using the mod functions, and then you are trying to look at a distribution, so you will get a distribution which has multiple kinks, so which shows certain steep changes in the behavior, right? So one of the fact is that it is not differentiable. So we'll come to differentiability a little later. But this kink in the in the absolute value, the kink in the change in the absolute value is something which is almost which is very noteworthy because it shows a flip in the behavior at a point of time. So basically, if you are trying to kind of get into flip processes or through flip changes, so you can let's say you are trying to do a trend changing mean or mean changing behavior, right? Or a variable which is kind of suddenly moving from low to higher, and there's a spike, and trying to do a very discrete or very abrupt change. Then that is you are trying to design that. That's where the modulus function will come into play, right? So you can design very steep regime changes. Regime changes in the sense like this, what you have seen over here, what we are seeing over here, right? So such steep regime changes can be modeled using the modulus function because this function generates a kink when the regime values are changing. So basically, you can so if your function or whatever function you are trying to optimize, if your objective function has a modulus function in that, you'll always expect a kink. You will not expect it to be a smoothly differentiable function. So the key limitation of this function is the lack of differentiability in this function structure, in this functional structure, right?
Okay, understood.
Shubham,
Yeah,
make
okay,
sense?
understood. Yes, yes.
Okay. Anyways, understanding this will be a cakewalk for you, Shubham. I get that.
No, modulus function. I can still remember some proofs related to this which I am not able to prove till date.
Anyways, you still remember the problems? I don't know of them. Anyways, chalo, let's move on. Okay, so a key important a key observation about this function is that key observation this function is that the function that the graph exhibits exhibits a kink in the kink at x equal to 0. At xi equal to 0. So using a modulus function can generate sharp kinks and is not often difficult to optimize using conventional optimization methods. Using conventional optimization methods, right? So this is one of the most widely used function, or this is one of the functions that we always see uh, in this part. So in this part of the exercise, you will always see how this function works. So in this side of market risk, so basically when we are kind of trying to look into the to assess the accuracy of the market risk models, or whenever we are trying to assess the absolute changes, the rate of changes, that's where we use this function. Right. So the next example that we come over here, so the next function that we talk about over here is the log function or the logarithmic function. Now, when I talk about the log function, so obviously the log and when I'm talking about the log function over here, I'll be talking about the log base 10, right? So I'm not talking about log of different bases. I'm just talking about the logarithm of base 10, right? So over here, as we talk about log function, we need to we need to talk about different aspects of this log function, because log function again is a very critical function to be used in this domain, because log is used for smoothing out fluctuations. Log helps us model the percent rates of percentage change, and hence is a very useful function for modeling uh, differentials or differential equations, or helping assess the dynamics. So there are a lot of different exercises that the log function. So there are different exercises that come about talking about while we talk about the log functions, right? Now again, with log functions and others, so there are so again there will be different kind of so different kinds of applications. We will kind of come to them over a period of time. So we see how the log functions look like as also. So this is the logarithmic functions, or as we call it, the log function. The log function. So over here we talk about let x, y be two real variables such that xy belongs to R, a function is a rule for which y is represented. A logarithmic function is such that is represented by the following rule. A modulus represented by the following rule. Log. Now with log function, one very important thing is that log function does not work on negative values, right? So if you define, let's say, if xi is less than 0, then log xi is undefined. So you cannot define a log function on the negative side of the Euclidean space or on that quadrant. So over here, this is for xi greater than 0. In fact, log is undefined for all xi is less than or equal to 0. Okay, so I have yi equal to log xi, which is this. So this function is defined or is positively is defined for positive values of xi, right? We say that the log function is defined for positive real values of xi. For xi, this function is not defined on the negative space, on the negative quadrant of the Euclidean space. The negative quadrant of the Euclidean space. So this is something very simple. So basically, if you have to plot a log function, what you need to do is you just need to check how the, so whether the xi is greater than 0. So so this function is only defined for positive real value. So in the negative quadrant of the Euclidean space, this function is not defined. So log 0 is undefined. Log less than 0 is if xi is less than 0, it's undefined. For xi greater than 0 but less than 1, log x is negative, and for values which is greater than equal to 1, log x is greater than, I mean, log x starts becoming positive, right? So so this function, the log function, works as follows. The log function works as follows. So yi log xi is less than 0 if less than 1. Right. So if this is greater than 0 and less than 1. So this is greater than 0 if this is and infinity. Right. So if it is greater than this, else undefined. So this is basically your so this is basically how your log functions would look like. So for between a 0 to 1, when this fractional, log x is negative. When it is greater than 0, log x is lying between 1 and infinity. Else it is undefined. So these are the two. So this is what the logarithmic function is. Now before we go to simulate the log function, what do we get or what do we talk about? So why does log function gets used? So for most of the cases, log functions are log functions are used. So number one, logarithmic transformations are widely used in time series data, in time series variables, uh, or in any of these quant modeling frameworks, because in fact whenever we are trying to assess the price, the the price of an index and its movement and all. So whenever we are trying to assess the percentage movement of the index and also, what we are always trying to do is we are trying to take we try to always take a logarithmic transformation of the variable. So for example, when stock prices are getting predicted, right? So stock price is predicted, or whenever I'm trying to stationarize a variable or trying to reduce the fluctuation in a time series, it is always the logarithmic transformation. So log transformation help me by not only reducing the fluctuation or the smoothing the data to some extent, but it also helps me to to linearize some of the tendencies, and then it also helps me in capturing percentage changes. So basically, whenever I'm trying to plot any derivative or any differential or any such evolution of a variable, I am always trying to use the basic logarithmic function, right? So that is where the log function comes into play, right? Okay, so after this, there are two more functions which we need to talk about. So one of the function is called the exponential function, because the exponential functions again will play a very critical role in terms of market risk variable, in terms of continuous variables like price series, in terms of because it would show the growth rate of the variable. So whether if you want to assess whether whether the variable that I'm trying to predict is moving in a exponential manner, or is it moving in a more than exponential manner. So all these are some of the factors which we need to, or these are some of the variables which we need to take into account. So exponential functions will always play a very critical role. So logarithmic functions, because one of the key distributions, one of the key probability distribution which is seen for stock prices or for most of the assets is the log normal distribution, right? So with the log function, there is a whole set of distribution which comes into play. So that is why the log function becomes a very, very critical function in this case, as well as the exponential function which is there. So using these two functions, we can always construct the log normal distribution, which is there, the Gaussian distribution. So basically, one of the biggest applications of the exponential function is the Gaussian distribution. So we'll talk about the Gaussian distribution, the log normal distribution. As we talk about these functions, we'll use them as examples, and we'll see the wide variety of areas where these two functions are used for market risk variables, right? So tomorrow we'll start off with the plotting the logarithmic functions, right? And then what we'll do is we'll start going deep into these functions. We'll see what are the areas where these functions are used, what are the properties of these functions, and so on, right? So let's regroup in tomorrow's session, and let's do that, right? So thank you guys. Thank you for your time today, and let's catch up. Bye.
Thank you.
Okay.